Hi, I hope that you are doing great. This is the fifth video that I am going to talk about another method of factoring polynomials. If you're following my YouTube channel, you probably know that there is a playlist on my YouTube channel called Advanced High School Algebra. This video is uploaded onto that playlist. In the descriptions below the video, you find 5 links. The first link, as is common to the videos of this playlist, gives you access to a PDF file containing a number of problems, including the final answers if applicable. As you might know, the next video that I will upload onto this playlist, nearly 1 week from now, will be a video that I will present and discuss all the detailed solutions to the problems of this file. The second link is the link to the PDF file of these notes that right now you see on your display. And in this lecture I will write down my explanations in between empty spaces that I have already provided in the file. In this file, the solutions to examples that I will present in this video are not included. I use iPad Pro together with Apple Pencil and GoodNotes 5 application to produce these videos. The content of the third link is exactly the same as the second one, except that this one is the GoodNotes file. I strongly recommend you to have one of these files available when watching the video. If you have access to a tablet with GoodNotes installed on it, then you can use the third link to download these lecture notes directly onto your tablet, as if you yourself have created them in the first place. Otherwise, you can use the second link to download the PDF version of these notes and print them. I think having the notes in front of you while watching the video could be very helpful in active learning. The fourth and fifth links are links to PDF and GoodNotes file accordingly of these lecture notes, but this time they contain all my solutions to examples and all my written explanations that I will present by the end of this video. At the end, I would say that I spend many hours enthusiastically to make these videos available for free. If you found the video somehow useful and enjoyed watching it, I would be thankful if you could give me a thumb up. By subscribing to my channel, you not only support me, but you will also be notified if I upload a new video. Okay, so now let us start today's lesson. If you remember, I have already talked about how to use identities to factorize polynomials. Yes, but then in that video I was using mostly the most famous identities to do the job for us. But now here, if you remember, I have already talked when I was talking about algebraic identities. I was also talking about these identities, which are not as famous as the other ones, but of course some harder problems somehow uses these identities to be solved. So for example, if you remember, this is useful when I have a trinomial and I want to raise it to power 3. Then that was the identity we came up. And then if you remember, this was one of the famous identities. I said that this is also very useful to know this identity. This is already a factorization of this expression, the sum of cubes minus 3 times the product. And then from identity number 2, we realize that we can have number 3, namely that if the sum of the cubes is equal to 3 times ABC, then it would imply that either the sum of these 3 numbers is equal to 0 or all of them are equal. And of course this arrow is double-sided, It means that if somebody knows that a plus b plus c is 0, immediately we can conclude that this is happening. Or if we know that a is equal to b is equal to c, we can immediately conclude that this is happening. And then we have three identities here. Okay, this is crucial that these identities are valid if a, b, and c are real numbers. But here, in these three identities, you need to be careful. A and b are real numbers, so they can be any number that you like. But then in this identity, n is a natural number, 1, 2, 3, 4, etc. In the second one, not only n is a natural number, but it has to be an odd natural number. So 1, 3, 5, 7, etc. And then in the last one, n has to be an even natural number, 2, 4, 6, 8, etc. Okay, and they are very similar, so make sure that you really understand them and not mix them up. Okay, so for example, here I have the difference of an minus bn for any natural n. Then I can write it as this product. So it is already in a factorized form because it's written in a product form. But then I will have nth root of the first one. This is minus, I put minus, the nth root of the second one. And I write the bigger brackets, the content of the bigger brackets in this form. I raise a to power n minus 1. This was n, this starts with n minus 1. And every time I lower the exponent of a by 1 unit and add the exponent of b by 1 unit. Okay? And continue until I reach to b to power n minus 1. So the pattern in the second pair of brackets for all of them are the same. For this second one and the third one, you need to be careful. Here the signs are all positive, but here the signs are alternatingly positive and negative. Negative, positive, negative, positive until the end, and this is the same, negative, positive, negative, positive until the end. Another crucial point that you need to remember here is that when n is odd, this an plus bn, on the right hand side we have a plus b. But when n is even, on the left hand side I have an minus bn, and then I have a plus b on the right hand side. And if n is even, so you see the last one ends with a negative sign. And that's clear because when n is even, if you start alternatingly changing the signs, then the last one becomes a negative number. Okay, of course, let me give you some examples that we can somehow use these identities. Okay, so factorize the following polynomials. Let me make this a little bit smaller so that you can see both identities and what I am writing here. Okay, so number one, you see I have this expression. I want to factorize this. Immediately you see that you can use this identity here, yes, because this is the sum of 3 terms to power 3, and then this identity will help me to write something for it. So let me just do that. So this becomes equal to, I use this identity number 1, I replace a here with x, b here with y, and c here with z, yes? So then what happens? This becomes x to the 3 on the right hand side plus y to the 3 plus z to the 3 plus 3 times x plus y times y plus z and z plus x. What I have written so far is the answer to this, is the expansion of this part. But then you see that I have minus x3, minus y3, and minus z3. So I put them at the end. But then it's very simple. You see, this expression actually this one cancels this term. This will cancel this one, and this will cancel that one. And then what is left for me is just 3 times x plus y times y plus z and then z plus x. Yes, and that's the end of the problem. Yes, this is written in a factorized form. It's written in a product form. So you see, sometimes it was easy to use this identity to factorize the polynomial. Let us solve the next problem that's more interesting. So you see, I want to factorize this polynomial. So what I want you to realize is that I want you to see how can I use the third part. How? So assume that you can replace A. Let us replace A with x minus y and B with y minus z and C with z minus x in this identity. Yes. Now if I ask you what is the sum of A plus B plus C, you would say A is x minus y, B is y minus z, and C is z minus x. So what can I see? I can see that this x and that x are cancelled, this y and that y and z, that z, so I will get 0. So I see that A plus B plus C is equal to 0. And see, look here, A plus B plus C is 0. I can go in this direction and conclude that the sum of cubes is equal to 3 times the product of those three numbers. Yes, so this implies that A to the 3 plus B to the 3 plus C to the 3 is 3 times A, B, C. Yes, so let me write it in brackets. But what is A? A is this expression, B is this expression, C is this one. So let us replace them here. So this will give me x minus y to the 3 plus y minus z to the 3 plus z minus x to the 3 is 3 times A times B times C. Yes? And look, that was my expression that I want to factorize. This is exactly this expression. It is equal to 3 times this product, and it is written in product form. So it means that I succeeded to factorize this polynomial very simply. Okay? So let me explain this. If I want to make it simpler for you, you see I have this thing plus this thing plus this is 0. So whenever the sum of 3 numbers is equal to 0, the sum of the cubes is equal to 3 times the product. And this will help you to factorize the polynomial. Yes? Okay, let me make it a little bit smaller so that you can see the polynomial. The next one, number 3. I want to factorize x to the 5 minus 1. But you can immediately realize that x minus x to the 5 minus 1 can be viewed in this way. Instead of 1, I can imagine that I have 1 to the 5 because they are the same thing. And then you immediately compare this one with this expression. You see, A is replaced by x, B is replaced by 1, and n, which is a natural number, is replaced by 5. So I can immediately use this. Okay, so then let me write everything in detail. So it becomes A minus B, but A here is x, B is 1. Then I start with 1 power less, 1 exponent less. So I will start with x to the 4. The next time I write x to the 3 and then I write B. What is B? B is 1. You don't need to write the details, but I want to make sure that you understand everything. The next one, I subtract 1. I did use actually, I deduct 1 unit from 3, it becomes 2, and then I will add 1 unit to the power of B. And then I do the same thing, it becomes x to the 1, 1 to the 3, and finally it becomes x0, 1 to the 4, and I will stop. But of course nobody writes it like that. We immediately simplify it to x to the 4 plus x to the 3 plus x to the 2 plus x plus 1. Yes, and this is already in factorized form. Yes. Okay, so let me do next one as well. So number 7. Here you see that x7, I have x7 plus 1, but I can write 1 to the 7 again. Yes, but now can I use this second identity, this number 5, to factorize this? Yes, if you compare this one with this one, you see that they have the same structure. A has been replaced by x, b has been replaced by 1, and n has been replaced by 7. But there is a condition here that should be met. And that condition is that n should be odd, which indeed is the case. 7 is an odd number. So everything is ready. I am allowed to use number 5. Yes? So what can I write? I can write x plus 1. And then I will start with x to the power of 6. But then not positive. You see, the signs are alternatingly positive and negative. So the next one would be negative. I write x5. I add 1 power to 1, but you know, as before, you see there is no rule for these ones to write. So let me just write x to the 5. And the next one would be positive x to the 4, negative x to the 3, positive x to the 2, negative x, positive 1, sorry. Positive 1. And that is the factorized form of this expression. Okay. Okay, I will take this question to the next page, and I will start from number 5, and finally I want to say something about even powers. Okay, so this is the same question, but here I start with number 5. Yes, so number 5, how can I write number 5? I can write it as x to the 5. Instead of 32y to the 5, I can write 2y to the 5. Yes? And everything is again in order. Yes, I can compare this one. So hopefully you can come with me to the previous page. So look here. I have x and I have 2y, but I have powers of 5 and I have plus here. So if I go back, this is exactly comparable to number 5 again. Yes, but a has been replaced by x, b has been replaced by 2y, and n has been replaced by 5, and 5 is actually acceptable here because it's an odd number. Yes, so I will follow the same rule. What can I write? I can write the 5th root of the first one plus the 5th root of the second one, and I start with x to the 4. But then alternatingly I have to change the sign, so I would write x to the 3, but then I will multiply it by 1 power of b, which is 2y here. Then I would write positive x to the 2, but 2y to the 2. So you see, the first exponent was 4, and then 3, then 2, then it becomes 1, and finally 0. Then the power of 2y here is 0, nothing. Then I have 1, then I have 2, 3, and finally 4. This is positive, the next one is negative, x, and then I have 2y to the 3, and then I will have 2y to the 4. Okay? But of course, I can simplify this, yes? What can I do? I can write it as, let me make it bigger now, we don't need that. Okay, so what can I do? I can write it as x plus 2y. X to the 4 is just x to the 4, but then 2y to the 1 is just 2y, so I would write it 2x to the 3y. And then I will have the next one is 4y squared times x squared is 4x squared y squared. And the next one is 8y3, so then it becomes minus 8xy3, and then you will have 16y to the 4. Yes, and this is written in factorized form. Okay, so for number 6, let me, if possible, let me do it in different ways. Okay, of course there are things that we can do for number 6. I can interpret it in this way. There are 3 ways that I can do this. Okay, x to the 4 minus y to the 4. So let us go back to the previous page. I can use this identity because for this identity what matters is that n is a natural number. It doesn't care if it is even or positive, even or odd. So I will use this to factorize that. Let us see how it goes. If I want to use number, what was the number? The number was 4. So if I use identity number 4, then what can I write? I can write x minus y, then I will start with x3, and then I would write x2y, then I would write xy squared, then I would write y to the 3. Yes? Of course, this is okay. But this is not fully factorized. Yes? For example, here you can take these two together. Let me change my color. So I can take these two together, and I can take these two together in a group. And then I can continue in this way. So this becomes x minus y. Then I take x2 out from the first group. It becomes x plus y. And then I can factor y2 out from the second group. It becomes x plus y again. And this is good because now x plus y and x plus y is a common factor, and I can pull it out. I had already x minus 1 there. I will pull x plus y out. Then what is left is x y squared plus y squared. Okay, and you know that I cannot continue here because if I want to continue, I have to do it on over the set of complex numbers. So this would be the end of this factorization. On the other hand, because now here n is even, I can also use number 6 because number 6 works if n is even. So, but remember, here the signs are alternatingly positive and negative, and even though this is negative, I have to start with positive if I want to use number 6. Okay, so let me write this one here. Let us do it the other way around. So I would write x to the 4 minus y to the 4, and then I put equality, but this time I am going to use number 6. Okay, so what can I write? I can write x plus y, and I start with 3 again, but alternatingly I have to change the signs. So x3 minus x squared y, positive xy squared, and negative y3 at the end. Again, this is also correct, but not complete. So what can I do? I can again take these two together and take these two together. So then what happens? This becomes x plus y. Then I will have x squared, and I have x minus y plus. From the second group, I can factor y squared out, and then I am left with x minus y. And then you can see that x minus y appears in both of them, so I can factor it out. I already had x plus y there, and then I will take x minus y out, and then I will have x squared plus y squared. And then you see that this is the same answer. Yes, as before. But I hope that you remember this is so elementary. This polynomial is so elementary. I prefer not to do any of these methods here. What should I do? I immediately recognize I have this difference of even powers, so it means that I have the difference of two complete squares. So the first thing that comes to my mind is to use the conjugate rule, not these identities. Yes. So here, if I want to do it, I would prefer immediately start with very simple conjugate pattern. Yes. So this time, let me write a conjugate identity. Okay, so then I immediately write x to the 2 minus y to the 2 times x to the 2 plus y to the 2. But then I realize x to the 2 minus y to the 2 is another conjugate identity, so I can write x minus y, x plus y, and then x plus y squared. And you see that this is the same answer, but much more efficiently done. It's much better. So I would say that this is the importance of this formula. First of all, this is an identity, mathematical identity. It is true, so it's worthy to know about that. I will give you an example that somehow we need to use this, but not for complete factorization, of course. If I want to factorize x to the 4 minus y to the 4, even though both of these are correct, but I would prefer to do it using the conjugate identity. And that is the content of this remark that I have already mentioned it. So as you saw in the last part of the previous example, to factorize an minus bn when n is even though it is possible to start with any one of the identities 4 or 6 above, you see, 4 or 6 above, but it would be simpler if one first applies the conjugate identity to an minus bn appropriate number of times. So here I did conjugate identity here, and let me write down here as well. So you see conjugate identity, I applied it 2 number of times here. Okay, so okay, now let me show you a totally different application of some of these identities. For example, in this example, I'm going to show that 2 to the power of 180 minus 1 is divisible by 9. Okay, so this is a huge number. Okay, but we want to show that very simple method that this number, whatever it is divisible by 9. Okay, so if you don't mind, let me bring the formulas in front of you. And unfortunately, this I have to bring all of it, so let me just copy this one and take these formulas with me here and make them very small, because at least it's better to have it in front of you. Okay, I hope that this is readable. Yes. Okay, so these were the identities we had on page 1, and then I want to prove that this number is divisible by 9. Yes. Okay, let us see. Of course, you need to have some experience of to know how to do in these kinds of problems. So I would write this one, number 1. 2 to the power of 180 minus 1 can be assumed to be 2 to the power of 180, and then I can write it as minus 1 to the power of 180. They are the same thing. Yes. Of course, if I just factorize it, and write it as 2 minus 1 times something based on this identity, it's a correct thing, but 2 minus 1 is just 1, and every number is divisible by 1. You don't need to prove that. But how can I generate 9? So 9 can be assumed to as 2 to power 3 plus 1 somehow. Yes, 2 to the power of 3 plus 1 gives me exactly 9. 2 to the power of 3 is 8. 8 plus 1 is 9. And then it reminds you somehow you need to make this combination appears. Yes. Okay, so this is also another name for that. You want to make this combination appear. So you have a negative sign here, but you want to end up with a positive sign. The only identity with that property is the last one. You see, here I have negative on the left hand side, but when I write it, it becomes positive. But there is a condition for that, and then the n should be even. Okay, so I would write it in this form. Instead of 2 to the power of 180, I would write 2 to the power of 3 and then to the power of 60. Yes, this becomes exactly 3 times 60, which becomes 180. And instead of 1 to the power of 180, I can do the same thing. I can write 1 to the 3 to the power of 60. Okay, now let us see what is going on. I would replace A with 2 to power 3. I would replace B with 1 to the power of 3. And I would replace N with 60, and 60 is even. Yes, so it means that I am actually respecting everything in the last identity. So then it means that if this is A, if this is B, and this is N, and N is even, I can use this formula to factorize it. So then I can write it as 2 to the power of 3. Look here, on the right hand side I have A plus B. So then it becomes 2 plus 3, 2 to the power of 3 plus 1 to the power of 3, multiplied by a very big number, very big brackets, yes. So what should I write if I want to write some of them? I should write 2 to the power of 3 to the power of n minus 1. So you see, it starts with n minus 1. So I would write 2 to the power of 3 to the power of 60 minus 1, which is 59. And then I have to change the signs alternatingly. So the next one becomes negative 2 to the power of 3 to the power of 58, and then 1 to the power of 3, which is my B. Let me write the next one as well. So it becomes 2 to the positive this time. I am changing the signs alternatingly. This becomes to the power of 57, and then I have 1 to the power of 3 to the power of 2. And then I will continue this process, and I will end up with negative 1 to the power of 3 to the power of 59. Of course, we really don't need to write these numbers, but I wrote it because I want to show that I am exactly following this pattern. But what is important now is that, first of all, what is this number? This number is 2 to the power of 3, which is 8, plus 1 to the power of 3, which is 1, and it gives me 9. And I don't care what is this number. What I care is that this number is an integer. Yes, an integer. This is for sure, yes. I don't know these numbers at all, but I know that every number involved here is an integer number. And I am raising them to some powers, multiplying them, adding them, subtracting them. So it is clear that what I will end up is an integer number. So let me call this integer number, I don't know, let me call it a capital Q. Then what happens is that this expression is 9 times Q. So now look, what I got. I got 1 to the power of 180 minus 1 is 9 times Q, and Q is an integer. So what does it mean? It means that this number is an integer multiple of 9. Any integer multiple of 9 is divisible by 9. So therefore, I can conclude that 2 to the power of 80 minus 1 is divisible by 9. So you see, this is one identity. This is one problem that I use this identity, yes, because do you remember I said in the previous page that usually using identity 6 for factorization is probably not that efficient. I could do it simpler using the conjugate identity. But this is also important to know that these identities exist because, for example, you see that I was able to use the same identity to prove this another type of problems. Okay, so let us do more or less the same thing. So you have a little bit of experience now, then I can use the same, more or less the same trick to solve the other one. So I have also provided you some of these examples in the exercises that you can work on them and then improve your skills to see how you can use these identities effectively. So let me number 2. So for number 2, I have 3 to the power of 52 and minus 2 to the power of 39. Yes. Then, for example, do you see any connection with these numbers and a common exponent? if you just see, you see that 52, let me change my color. So 52 can be written as 4 times 13, and 39 can be written as 3 times 13, yes? So this common factor is actually 13, yes? So what can I write? I can write this as 3 to the power of 4 to the power of 13, and then I will have 2 to the power of 3 to the power of 13, yes? So this is another way of writing exactly the same thing, yes? But what is 3 to the power of 4? 3 to the power of 4 is actually 81 to the power of 13, and 2 to the power of 3 is 8 to the power of 13, yes? And then look here, if you use this identity, a to power n minus bn is always equal to a minus b multiplied by these terms, where n is any natural number here. We don't care to be even or odd, so this is an integer here, yes? This is a natural number here. So I can use that identity and write it as 81 minus 8 multiplied by 81 starting with power 12, and then I would write positive 81 to power 11 multiplied by 8. I would write 81 to the power 10 multiplied by 8 to the power of 2, and then I will continue to 8 to power 12. Again, if you look here, this number is exactly 73. Okay, so I would write it as 73. Let me change the color. So 73. And what is important for me is this expression. I don't care about the exact value of this. What I care, this is an integer again. So then again I can call it q. So then it means this is 73 times q. So what does it mean? It means that this number 3 to the power of 52 minus 2 to the power of 39 is 73 times q. Q is an integer. Yes? So this means that 3 to the power of 52 minus 2 to the power of 39, which is an integer multiple of 73, is actually divisible by 73. Yes, is divisible by 73. Okay? Okay, now here in method number 9, I want to talk about how can symmetry of the polynomial help us to factorize the polynomial. Of course, first of all, I need to define what do I mean by symmetry in a polynomial. Okay, I only restrict my discussion to cases of 2 variable and 3 variable polynomials. I will do the 2 variable case in this video, and I will postpone talking and discussing about the 3 variable case in the next video. Okay, so let us formally define what is the meaning of a polynomial in 2 variables being symmetric. Yes, we say that a polynomial qxy, a polynomial q in 2 variables x and y, is said to be symmetric if the q of x and y is exactly identical with q, y, and x for all possible values of the variables x and y. Namely, if these two are identical. So what does it mean? I give you a polynomial in x and y, you interchange x and y, you swap them. In principle, you might get a new polynomial. But if in this case you get the same polynomial back, then that polynomial is called a symmetric polynomial. Let me give you, the idea is very, very simple. Let me give you examples. Here, each one of these polynomials that you see here are symmetric polynomials. Of course, probably this one and this one are the simplest possible symmetric polynomials. Why this polynomial is symmetric? The reason that this is symmetric, for example, number 1, what happens if I interchange x and y here with each other? So what is q1 of y and x instead of x and y? So it means that wherever you see x, you put y. Wherever you see y, you put x. So you get y plus x. But you know that there is no difference at all between y plus x and x plus y. And that is exactly your polynomial qx and y. So roughly speaking, if I swap x and y, the result is the same as before. And you see here it's the same. If I interchange these two, this becomes y times x. But there is no difference between y times x and x times y. Yes. So what about number 3? Number 3 is also a symmetric polynomial. Yes. So let us check it in detail. So number 3. So if I calculate q3, but if I change y and x, interchange them, then instead of having x minus y to the power of 2, I will have y minus x to the power of 2. Yes, but this is the same thing as x minus y to the power of 2, yes, because I have an even power. So if you want, I can write more details to it. So I can factor a negative sign out, then it becomes x minus y to the power of 2. Then I can interpret this as minus 1 times x minus 1 to the power of 2. Then it means that I have minus 1 to the power of 2 multiplied by this to the power of 2. But minus 1 to the power of 2 is just simply 1, and 1 times x minus y to the power of 2 is the same. And then it means it is exactly the same polynomial. So this is exactly equal to q3 of x and y. So you see that by swapping x and y, this polynomial, the resultant polynomial, is the same as the original one. So this is also a symmetric polynomial. And then hopefully, so let us, for example, convince ourselves that q4 is also a symmetric polynomial. So what should I do? I need to calculate q4, and then I would write y and x. I will put y instead of every x, and I will put x instead of every y. Yes. So here you see I start with x squared. Now I would write y squared. Then I have y squared. I would write x squared. Plus I have 3 times x to the 2, and then times y. I would write y to the 2 times x. Then I would write 3xy squared. I would write yx squared. Yes, but hopefully you can immediately see that this expression and that expression are identical. Yes, because y squared plus x squared is another name for x squared plus y squared. And then I can write this term first, and I would write them in an appropriate order. X squared y, and then I would write 3xy squared, and that's exactly q4 of x and y. Yes. So you see here, let us just convince ourselves that nothing will change here if I interchange x and y. So this x6 becomes y6, y6 becomes x6. This term transforms to this term, and this term will transform to that term. And here x will go and sit instead of y go and sit instead of x. And then 5 is just a constant, nothing will change if I interchange x and y. So you see that this is also a symmetric polynomial. This is also a symmetric polynomial. This becomes y plus x to 7 minus y to the 7 minus x to the 7. But if you look here, this is exactly the same as your original polynomial. So what I have written here, all of them are symmetric polynomials in 2 variables. And as I mentioned before, these are the simplest possible symmetric polynomials in two variables that we can imagine. There are no simpler than that. there are no simpler polynomials, symmetric polynomials than that. And let me give you some non-examples. So for example, this one is not a symmetric polynomial. Why? Because if I interchange x and y, then what will I will get y minus x. But hopefully you can immediately see that y minus x is not equal to x minus y. So this polynomial is not symmetric. Here, if I interchange x and y, then what I will get is 2y plus x. But it is completely clear 2y plus x is not identical with 2x plus y. Here the coefficient of x is 2, here the coefficient of x is 1. The coefficient of y here is 1, and the coefficient of y here is 2. So they are not symmetric, and this one is not symmetric. So because if I interchange x and y, then what will happen, this becomes y squared plus x squared. Then so far so good, nothing has changed, but then the next term becomes 3y squared x plus 4yx squared. Now this is not identical as before. Even though this part remains the same, that's okay. But look here, if you look here, you have xy squared. Here you have xy squared. But here the coefficient of xy squared is 3. Here the coefficient of xy squared is 4. So it is completely clear that these two are not identical. And hopefully you can convince yourself that this is not symmetric as before. Okay? Okay. Now let me introduce two more definitions for you here. So there are some terminologies that you need to know. Elementary symmetric polynomials in two variables, and the power sum symmetric polynomials in two variables. I want to introduce them to you. As I told you before, x plus y and xy are the simplest possible symmetric polynomials in two variables. And mathematicians have actually given them names. These are called elementary symmetric polynomials. You cannot find more elementary symmetric, more simpler symmetric polynomials in two variables than these two polynomials. One of them is by the way, this is a standard symbol used in the literature. So you call it E1 xy, and that is x plus y. And the other one is E2 xy, is x times y. These two polynomials are famous ones called elementary symmetric polynomials in two variables. We reserve this symbol E1 for x plus y, and we reserve this symbol E2 for xy. One thing that I want to mention is that in these cases, these indices, these subscripts, are actually referring to the degree of the corresponding polynomial. If I ask you what is the degree of this polynomial, you would say the degree is 1. Yes, because the highest power of the variable appearing here is 1. And if I ask you what is the degree of this polynomial, of course, if I ask you the degree of polynomial with respect to x, you would say 1. With respect to y, it is 1. But when we talk about degree of the polynomial, I would mean the sum of these powers, which is 2. So if I ask you what is the degree of this polynomial xy, you would say 2, and this subscript indicates that. And if I ask you what is the degree of this polynomial, you would say y, and the subscript indicates that. Okay? And then if there is no matter of confusion, instead of x plus y, instead of writing it with E1 x and y, I just simply write E1. So whenever in the coming parts, when I talk about E1, I mean x plus y, and when I write E2, I mean x times y. Okay? There is also another piece of terminology that I want you to know, and that is power sum symmetric polynomials. So for any natural number n, a polynomial p sub n x and y defined in this form, x to power n plus y to power n, is called the power sum symmetric polynomial of degree n in two variables x and y. Yes, of course, if I ask you what is the degree of this polynomial, you would definitely tell me that the degree is n, because the highest power appearing there is n. And if I ask you, is this polynomial indeed a symmetric polynomial, you would say yes, because if I interchange x and y, then I will get x to the power of n, x to the power of n, which is identical to what I have here. So this is indeed a symmetric polynomial, and because this is the sum of powers, this is called power sum symmetric polynomials. And because its degree is n, we say that this is a power sum symmetric polynomial of degree n in two variables x and y. So again, here as before, this subscript indicates the power of the polynomial, of the degree of the polynomial, and from now on I just write Pn. When I write Pn in what is coming, I always mean x to the n plus y to the n. Okay? Okay. So let me just read this one for you. Lemma 17.11. Every power sum symmetric polynomial Pn x to the power of n plus y to the power of n, the one that I just introduced, can be expressed as a polynomial in e1xy and e2xy. So do you remember e1 was x plus y and this e2 was xy? Okay, so it means that I can always write this expression for any value of n, yes, in terms of e1 and e2. Let me explain a little bit about this word lemma. Lemma, theorem, corollary, propositions, you can see this in mathematics books. They all mean true statements, yes? But usually theorems, we call a very important statement to be a theorem. Yes? And what's the meaning of a lemma? A lemma is a true statement that we usually prove before a main theorem coming, and this will needed in the proof of the main theorem. So somehow it means that because the proof is supposed to be complicated in the main theorem, we split it into different parts, and each one of these true statements coming before the theorem is called a lemma. So when you see this lemma, it means that you should expect a more important theorem is coming next, and moreover, in the proof of that more important theorem, at some point we probably are going to use this statement here. But except for this, lemma is just a true statement. So some statement, yet still you can rely on. Okay? So lemma is a true statement, so it needs a proof. Okay, but before proving this in general, let me first try to convince you what is the and then try to make it clear what is the content of the theorem. So the theorem tells you that whatever you choose for this value n, for any natural number n, this expression is always expressible in terms of e1 and into e2 as a polynomial. So not, for example, a square root of e1 plus e2. If I write p equals to this, I would also say that p is written in terms of e1 and e2, but this is not a polynomial. What I mean is that this pn can always be written as a polynomial in which the variables are e1 and e2. Let us try to discover the content for very special and simple cases. So let us consider P1 first. What is P1? P1 means n is 1. So this becomes x to the 1 plus y to the 1, which becomes x plus y. But what is x plus y? X plus y is exactly e1. Yes? So this becomes e1. Yes, it was possible. So P1 is expressed in terms of e1 and e2, here in only e1 of course, as a polynomial. Let me go to p2. So what is p2? How can I express p2? p2 is x to the 2 plus y to the 2. Yes, here Pn is x to the n, y to the n. So P2 means x to the 2, y to the 2. But if you remember from the previous lectures on algebraic identities, we can write it as x plus y to the 2 minus 2xy. Yes, if you have forgotten that, this is very easy. This becomes x to the 2 plus 2xy plus y to the 2, and then you have minus 2xy. This one and that one are cancelled, so what is left is x squared plus y squared. So what I have written here is completely correct. But then let me ask you, what is this expression? This expression is e1 and this expression is e2. So then you can see that this is e1 to the 2 minus 2 e2. So let me write them in front of them. So p1 was expressed to be just e1, and p2 is equal to e1 to the 2 minus 2 e2. Let me do one more case. Okay, so p3, you see p3 is x to the 3 plus y to the 3, yes? And then if you remember again in the algebraic identities, I introduced you an identity like this, x plus y to the 3 minus 3 times xy times x plus y. Again, if you have forgotten this, I hope that at least you remember this binomial identity. So it becomes x to the 3 plus 3x squared y plus 3xy squared, and then plus y cubed. And if I multiply this, it becomes minus 3x squared y minus 3xy squared. And these are cancelled, and what is left is x to the 3 plus y to the 3. So this is completely correct. But then what can I write? This is e1, this is e2, and this is e1 again. So you see everything is expressible in terms of e1 and e2 as a polynomial. So then it becomes that p to the 3 is e1 to the 3 minus 3e1 times e2. At least for these simple cases, we did it. We were able to actually express p1, p2, and 3 in terms of e1, e2. In all cases, this is a polynomial in terms of e1 and e2. But we want to prove that this is not just a coincidence. This can happen for all possible values of n. Okay, but of course, all possible values of n means that I have infinitely many possibilities. It's completely clear I cannot do it case by case. I can only do case by case things when I have finitely many things, then I finish at some point. If I have infinitely many numbers available, I cannot check it one by one. So I need to come to an argument that somehow can convince ourselves that this is going to continue. And this will cover all possible values for n. And this I would probably, it's good to at this point to present a formal proof. Okay, so how can I prove that this is always the case and this is not just a mere coincidence? Okay, the idea is to start from this. So let me consider Pn. So let me change my color. So let me consider Pn. We know what is Pn. So let me consider Pn minus 1. Yes, so let me consider Pn minus 1. Pn minus 1 is equal to x to the power of n minus 1 plus y to the power of n minus 1. Yes, and then let me multiply both sides by x plus y. By the way, is that clear? Pn is x to the n, y to the n. So p sub n minus 1, it means that I replace n minus 1 instead of n everywhere. So this is the meaning of p sub n minus 1. And then I multiply both sides by x plus y. Yes. And then I keep the left-hand side as it is for the time being, but I multiply the right-hand side term by term. So this becomes x times xn minus 1 becomes x to the n, plus the next one is x yn to the y to the n minus 1 plus yx to the n minus 1, and finally I have yn. Then again, let me keep the left hand side for the time being as it is. But let me put these two next to each other. So let me collect them in a pair of brackets. And then between these two, I factor xy out. So what is happening now? This becomes xy. Let me write this one first. Okay? I pulled y out here, and I pulled an 1x out here. I have n minus 1 x's. One of them I pulled out, so I am left with n minus 2 x's. And the same thing for the next term, I will be left with y to the n minus 2. Now, let me write everything here. So what is this one? If I ask you what is this, you would say this is E1. If I ask you what is this one, you would say this is E2. If I ask you what is, I made a small mistake here. Sorry. This is not N. You see here, this N minus 1. So this is N minus 1 here, not N. So let me correct it. This is N minus 1. Okay, so now if I ask you what is this, you would say this is Pn. This is already Pn minus 1. And if I ask you what is this, you would say that this is exactly P, but the powers are n minus 1. The exponents are n minus 2. So this is P sub n minus 2. Okay, so if I rewrite them, this becomes E1 Pn minus 1. On the right hand side I have Pn plus E2 Pn minus 2. Then what I do, I move this term to the left hand side. So then it becomes E1 P sub n minus 1 minus E2 P sub n minus 2 is equal to Pn. So let me write it in a, so Pn is equal E1 Pn minus 1 minus E2 Pn minus 2, and then this happens only when n is greater than or equal to 3. Yes, why is that? Because you see, I want to call this Pn minus 2. The P only makes sense if the powers are natural numbers. So it means that n minus 2 should be at least 1. So this means that n should be at least 3. So n cannot be smaller than 3. So the formula that I wrote here is always true if n is greater than or equal to 3. Okay, but how this will help me to prove the theorem? In principle, the right way to do the proof is what we call mathematical induction. The essence of mathematical induction is what I am introducing here, but I don't want to formally use mathematical induction to distract you, okay? This is beyond the scope of this lecture. Might be in the future I will cover also those parts of mathematics. But for the time being, you don't need to formally know about mathematical induction to be able to follow my argument here. Okay, I want to convince you that all P's can be expressed in terms of E1 and E2 only. I did it manually with P1 and P2. Forget about P3, I don't need that one now, even though I have done it. I did P1 and P2 manually, and you have to be convinced now that P1 is expressible in terms of E1 and E2, only E1 in this case, and P2 is expressible in terms of E1 and E2. Now, look, Let us look at this one and try to see what happens for P3. So what is P3? P3 means that I replace n with 3. So then this n minus 1 becomes 2, n minus 2 becomes 1. So let me just write this formula, because this formula is valid for all values of n greater than or equal to 3. So it means that this is also valid for 3. I'm just writing that formula for 3. So this becomes E1 P2 minus E2 P1. Yes? The point is that, look, I am not going to calculate this. I am going to convince you that P3 can be written solely in terms of E1 and E2. Okay. Is P1 is it possible to express P1 only in terms of E1 and E2? Yes, we did it manually here. So this is expressible in terms of E1 and E2. Is P2 expressible in terms of E1 and E2? Yes, we did it manually. Yes? Okay, so this is something E1, this is something related to E1 and E2. And then I have E2 and E1. If you look here, everything is either E1 or E2. Yes, so I succeeded. P3 is expressible in terms of E1 and E2. As a polynomial, by the way, because P1 is a polynomial, P2 is a polynomial. This is just integer, the natural powers of E1 and E2 here, the same thing. So that is also a polynomial in terms of E1 and E2. Okay, so I am convinced now that P3 is expressible. Yes. Now, let us go to P4. Using this formula, can I use this formula for P4? Yes, because this is valid for all possible values of n greater than or equal to 3, and 4 is also greater than 3. So I can use this formula for P4. If I replace n with 4, this becomes 4 minus 1, 3. This becomes 4 minus 2, 2. So then what can I write for P4? P4 is E1 P3 minus E2 P2. But now look, I am not going to calculate this for you explicitly, but I want you just to convince you that this is expressible in terms of E1 and E2. Let us check that. Is P2 expressible in terms of E1 and E2? Yes, we did it manually. Is P3 expressible in terms of E1 and E2? Yes, we just realized it in the previous step. You see, this is the check mark. So, okay, P3 is now, I know it's expressible in terms of E1 and E2. P2 is expressible in terms of E1 and E2. And look, these are just E1 and E2. So again, everything is in terms of E1 and E2. So P4 is also expressible in terms of E1 and E2. Let me just do one more step. So what about P5? Here, instead of n, I put 5. Then I will get E1 P4 minus E2 P3. Is E5 expressible in terms of P1 and P2, E1 and E2? The answer would be yes. Why? Because P4 is expressible in terms of E1 and E2. Why? The previous step. I convinced you in the previous step that P4 is expressible in terms of E1 and E2. What about E3? Yes, but this is two steps back. I convince you here that P3 is also expressible in terms of E1 and E2. So again, this is E1 and E2, this is E1 and E2, and everything here is expressible in terms of E1 and E2. So it means that P1 is also expressible in terms of E1 and E2. And I hope that you can see that this process can continue forever. And it will cover all possible values of n. At least you can see this mechanism will work for higher values of n. Yes. So to write it in a really formal way, I need to introduce it through the mathematical induction, but I want to avoid it. But the essence of mathematical induction is exactly what I have written here. Okay? So hopefully now you are convinced that every Pn can be expressed in terms of E1 and E2 as a polynomial. Okay, but look, I didn't calculate anything for you. If you ask me what is P5 in terms of E1 and E2, I am not done yet. I have to sit down, be patient, and calculate. Yes, only then I can tell you that I have P5. Let us check that one. You see, I didn't involve with explicit calculation. I just used a very simple recursive relation. These types of relations are called recursive relations, in which one term of a sequence of numbers, polynomials, or anything is related to the previous terms. These kinds of relations are called recursive relations. I just use this simple recursive relation to convince you that it is possible to express every Pn in terms of E1 and E2. But if you ask me what are the explicit way of writing them, I don't know yet. If you insist, I have to be patient, sit down and calculate. Okay, let us do it, for example, for P3. So, of course, we already did it for P3 in a different way, but now let us use this formula for P3. So what is P3? P3, so this is not part of the proof, so let me change my color and I can write it. This is not part of the proof. So the proof is finished here. So the end of the proof is here. Now I want to see some other aspects of this problem. So P3 is E1 times P2. The only thing that I have to manually calculate are just P1 and P2, and I have already done that. So P2 is this expression, P1 is this. So I just plug them in. So this becomes E1 to the 2 minus 2E2 minus E2 times P1, but P1 is again E1. And if I simplify this, this becomes E1 to the 3 minus 2E1E2 minus E2E1. And simplify it one more step, it becomes E1 to the 3 minus 3E1 E2. And that is exactly the answer we got it here using this direct method. And let me calculate P4 for you as well. So if you insist that I have to calculate P4, I can use this simple recursive relation, but you see I couldn't calculate P4. Let me just write it for you. This becomes E1 P3 minus E2 P2. So in order to calculate P4, I have to already calculate P3 and P2. I cannot jump directly to P4 using this method. I have to be patient, do it step by step, and then progress one step at a time. So here, what I can see is that now E1, instead of P3, I just calculated P3 here, so I just plug it, it becomes E1 to the 3 minus 3E1 E2, and then minus E2, I already knew what is E2, P2, I put it here, so then it becomes E1 to the 2 minus 2E2, and then I would simplify, so multiply, it becomes E1 to the 4 minus 3E1 to the 2E2 minus E2E1 to the 2 plus 2E2 to the 2. And then you see that these two terms are similar, so I can simplify that. It becomes E1 to the 4 minus 4 E1 to the 2E2, and then finally 2E2 to the 2. So you see, actually writing them explicitly in terms of E1 and E2 is another thing. Proving that this is possible is another thing. In this theorem, I just showed that this is possible. Theoretically, it's very important. Every one of these polynomials are expressible in terms of elementary symmetric polynomials as a polynomial. Yes. Okay. And now let us go to the next page. Here in this remark, I have listed for you P1, P2 up to P10. So P1 we already knew, P2 we already know, P3 and P4 I calculated. If you see here, if you go back here, we were able to calculate exactly this one. E1 to the 4, 4E1 to the 2E2, and 2E2 to the 2, yes? And that's exactly the same thing. And then using, so you see, I calculated P1 and P2 manually, use the recursive relation, relation together with P1 and P2, I was able to calculate P3. Okay, now using P2 and P3 and the recursive relation, I was able to find P4. If I want to find P5, I use P3 and P4 and the recursive relation and finding P5. So you see that I can in principle do it step by step until I reach to P10. Okay? Of course, you might think that is there any formula that can give me directly some order? For example, can I immediately calculate P10 without going into these long steps? Yes, the answer is yes, and this British mathematician Edward Warning, 18th century mathematician, actually discovered the following closed formula. So it is possible. So there are many things that might be distracting at this level. I don't want to confuse you with these things. So I just put it here for completeness. I want to show that, okay, yes, there is a formula that you can calculate them directly without going step by step. But you need to know a lot of things. So you need to know what is the meaning of sigma notation. Sigma notation is meaning adding terms together somehow. And this exclamation mark is what is called factorial. So for example, when you say 3 factorial, what we means to write 3 times 2 times 1, which is 6. I don't know, when we say 5 factorials, it means write 5 times the previous number, previous number, previous number up to 1. And if you multiply that, for example, it becomes 120. That's the meaning of factorial. And then E1 and E2 are just those polynomials, elementary symmetric polynomials. And then what is this symbol? This is called the floor function. So what does it mean? When I write the floor of an integer, say 5, it becomes 5 by definition. The floor of -3 is again -3. But if I ask you what is the floor of 2.5, it goes to the left and pick up the highest value, the highest integer value. So if you go from 2.5 to the left, the highest integer value, that the first integer that you reach is 2. So the floor of 2.5 is 2. I don't know, the floor of 2.1 is also 2. The floor of -2.1 is -3, because if you go from -2.1 to the left, the first integer that you meet is -3. Okay, and then Pn is just this P, yes, and this n that appears is just that subscript. Okay, anyway, I don't want to distract you with this formula, but I want you to know that there is a closed formula that you can write these expressions immediately. But what I want to describe here, so let me just clean them. What I want to draw your attention to is that could we, for example, somehow come to these general formulas? I'm not talking about the coefficients. Yes, the coefficients is something else, but can we come to these general form for these terms? Yes, so what do I mean? Let me explain. So P4 that I am, for example, let us consider P4. P4 that I want to calculate is x to the 4 plus y to the 4. What is the degree of P4? The degree of P4 is 4. So when I write equality, on the right hand side I should also have a 4th degree polynomial, because the left hand side is of degree 4. But how can I generate a 4th degree polynomial only using E1 and E2? The degree of E1 is 1. The degree of E2 is 2. We don't have any higher degrees. Okay, so let us look. Number 4, 4 I want to split 4 into the sum of 1s and 2s. Okay, so the first thing that comes to mind is that I can add 1 4 times. This is called partitioning 4. I partitioned 4 into 4 1s. Okay, this means that this corresponds to E1 times E1 times E1 times E1. Why? Because the degree of E1 is 1, this is also 1, this is also 1, this is also 1. All of them are of degree 1, and if I multiply them, if you remember in the lectures for polynomials, I told you that the degree of the product is the sum of the degrees. So the degree of this would be 1 plus 1 plus 1 plus 1, which is 4. So we expect that this combination might appear on the right hand side for P4, and indeed it appears. Yes, because this means E1 to the 4. Now, can I partition 4 into a sum of 1s and 2s? Yes, because the only degrees available are 1 and 2. Can I write it in a different way? Yes. For example, I can write 1 plus 1 and 2. Again, I will produce 4. This corresponds to E1 times E1 times E2. Yes, the degree of this one is 1, the degree of this one is 1, the degree of this is 2. So the total degree is 1 plus 1 plus 2, which is again 4. And this will correspond to this term, E1 to the 2, E2. You see, again, E1 to the 2, E2 appears here. But this is not the only possibility. Yes, I can write it another way. I can write it 2 plus 2. Yes, so then this means that this is E2 times E2. Then it becomes E2 to the 2. And you see that you have E2 to the 2 here. Yes, can I write it in a different way? Of course, you might think that yes, I can write it of 3 plus 1, but this is not possible here because I do not have any polynomial of degree 3. I have only E1 and E2. I know based on the theorem that I am able to write P4 in terms of E1 and E2 only. So it means that the highest degree that will appear is 2. So there is no 3 involved. Yes. So these are the only possibilities that I can write 4 as a sum of a number of 1s, a bunch of 1s, and a bunch of 2s. These are the only possibilities. Okay. To make this idea a little bit more clear, let me just do the other one for 5, for example. Yes. So assume that you want to write P5, which is of degree 5. Which terms do you expect to see on the right hand side for P5? Yes, 5, I want to split 5, the terminology is partition 5, into a sum of 1s and 2s. Yes, so the first thing that comes to mind is to write 1 5 times added together. So this corresponds to E1 times E1 times E1 times E1 times E1, which is E1 to the 5. So this is one of the terms that you expect to see on the right hand side for the formula for P5. What is the other possibility? Be careful, you are not allowed to use numbers higher than 2. So you might say that I combine 2 1s together and I will write 1 1 and 1. This is one possibility. And you do not repeat this one because that is the same thing. Yes. So I don't repeat. When I write this one, that's only. So this corresponds to what? This corresponds to what is E2? E2 is representative for E2 because that is degree 2. So this means that this is E2 1 time, but E1 3 times. So this is E1 to the 3 E2. So you expect to see this term on the right hand side. And then is it possible to do it the other way around? So I have 2, yes, I'm not allowed to go, okay, I can write one more thing. I can write 2 plus 2 plus 1, yes? I'm not allowed to use numbers higher than 2. Okay, so this means that I will have E2, E2 two times, but E1 one time, so it becomes E1, E2 to the 2. You also expect to see on the right, this on the right hand side. Yes. Is there any other possibility? No. So these are the only possible terms that you expect to see on the right hand side for P5. And then this is indeed the case. You see here P5. E1 to the power of 5 as we predicted. E1 to the 3 times E2 as one we predicted. And finally E1 times E2 to the 2 as we predicted. Yes. So I was saying that even without looking at the formula, you don't need this Edward Warning formula or other detailed calculations. You in principle can immediately write that P5 by this kind of very simple argument should be a combination of these terms. So I would write this is some number which I don't know. Of course the coefficients I don't know yet. This is to the 5, and then I will have B E1 to the 3 E2, then C times E1 E2 to the 2. So what I'm trying to say is that if we take that lemma, it tells you that P5 is definitely expressible in terms of E1 and E2. And by this kind of argument dealing with degrees, I was just able to find the very good form, the format of P5. Yes. And of course, if you want, you can also calculate these coefficients by a trick. And what the trick is, you can use particular values, special values. For example, you can choose x equal to 1, for example, and y equal to 0. Then if you put this on P5, this becomes 1 to the 5 and 0 to the 5. It gives you, for example, 1. So the left hand side becomes 1. But what happens for the right hand side? E2 becomes 0. So this term and this term will cancel. E1 becomes 1, and 1 to the 5 is what? Is 1. And then it means that A is 1, and that is right. You see, A1 is 1. Okay. But I don't want, so I just want to make sure that you understand this is important. So as soon as I know that P5 is expressible in terms of E1 and in E2, I can immediately, without very complicated formulas, I can use this kind of argument to guess what is the general form of that polynomial which is supposed to express P5 in terms of E1 and E2. That's also very important to know about. Okay, now let us go to the main theorem. Let me read it for you first. Every symmetric polynomial in two variables x and y can uniquely be expressed as a polynomial in E1xy and E2xy. Okay, so you probably understand that the claim is more broad in this case. So if we go back to the lemma only claims that these type of symmetric polynomials, power-sum symmetric polynomials, can be expressed in terms of E1 and E2. But now we go further. We now claim that not only those type of symmetric polynomials can be expressed as a polynomial in terms of E1 and E2, but also all possible polynomials in two variables that you can imagine can be written as a polynomial in E1 and E2, and this is unique. If you can write it in only one form in terms of E1 and E2. I only just try to motivate the proof for the possibility of this thing to happen. I want to show that every symmetric polynomial can be expressed as a polynomial in terms of E1 and E2. Proving the uniqueness is somehow technical, and I will skip that part. Okay. But let us understand why it is possible to write all possible symmetric polynomials in terms of E1 and E2. Okay, let us consider, for example, So let me write sketch of a proof, or somehow the proof of the first part only. So let P qx and y be a symmetric polynomial. Okay, what are the possible terms involved in this polynomial? You might have a term in this polynomial. If you go look inside your polynomial, it is possible that you see a term in this form, ax to some power m. Yes, but because this polynomial is symmetric, if you see this term somewhere in your polynomial, definitely you will also see a similar term for y. Yes, if you have this term in your polynomial, but you don't have this term in your polynomial, then it is not symmetric. It cannot be symmetric, because if you switch this x to y, then you will have aym. And if aym is not there, this is not a symmetric polynomial. So I'm telling that these two things come in pair, and be careful that the coefficients have to be the same. If I have 3x to the power of 5, and if I have 2y to the power of 5 with different coefficients, this cannot be a symmetric polynomial. Because if I interchange x and y, this becomes 3y5 and this becomes 2xy5, and they are not the same. Okay? So what I'm trying to say is that if you see a term like this in your polynomial, definitely you will also have a term like this. The other way around, if you see a term like this in your polynomial, you definitely have this. So these things come in pairs. So this is one possibility that you might have. Okay? But if this happens, between all these type of terms, you can factor the coefficients out. And if you factor the coefficient out from here, it becomes x to the m, y to the m. But look, what is this one here? This is just simply a powersome symmetric polynomial. So this is APM. But in the lemma, as I told you, lemma comes before the main theorem. In the lemma, we showed that every powersome symmetric polynomial can be written as a polynomial in terms of E1 and E2. And then I am done here, yes, because if this is written in terms of E1 and E2 multiplied by a constant, it is still written in terms of E1 and E2. So it means that these type of terms that appears these type of terms that appear in your polynomial can be expressed in terms of powersome symmetric polynomials, and powersome symmetric polynomials can be expressed in terms of E1 and V2. So we are done, at least for that part of my polynomial. Another possibility that might arise in your polynomial is this. So you might see a term like this, x to the m, y to the m. It is possible to have a term like this. It doesn't violate the symmetry of the polynomial. Why? Because here, if I interchange x and y, then it becomes a y to the m, x to the m. Yes? And this is exactly the same thing. So it might happen that I have these type of terms in my polynomial. But then look, this is already expressible in terms of E1 and E2. Why? Because this can be written as a xy to the power of m. But what is xy? Xy is just E2. So then you can see that this is a e2 to the m. So it is already expressible in terms of E1 and E2. By the way, let me just write this one here for you as well. PM can be written as a polynomial in E1 and E2 based on the previous lemma. Based on the lemma. There is only one lemma in this video. Okay, But there is also one other type of possibility that might happen here. What is that one? It might happen that I have terms like this, but the powers are not the same. Okay? For example, you might have you might see, when you're looking into your polynomial, you might see a term like this, where m and n are not equal. Okay. For example, for definiteness, let me assume that m is greater than n. It doesn't matter, you can assume the other way around. But again, look, this on its own is not symmetric. If this is alone in your polynomial, it will violate the symmetry of the polynomial. Why? Because I have assumed that m and n are not the same. So if I interchange x and y together, then it becomes then it becomes a y to the m, x to the n, and they are not equal. Okay, so it means that if something like this happens, if this term is present in my polynomial, then definitely this term is also there, a x to the n, y to the m, with the same coefficient. If this is there, this also should be there. Okay, so it means that I have this type of terms in my polynomial. But then what happens, I have assumed that m is greater than n, so I can factor a xn, yn out. Okay, yn and a are already pulled out here. xm is a higher power. I have pulled out xn, so what is left is x to the power of m minus n. And for the same reason, the second term, what is left for the second term is the same thing, yes? But I can write it in this form. I can write it as a xy totally to power n, and then I repeat the second factor. Yes, and then look what happens. This I can write it in this form. This one here is just e2 again, so I can write it as e2 to the n multiplied by, what is this one? This is a power sum of degree m minus n. So what I can write this as p sub m minus n. But again, this is done, yes? This is in terms of e1 and e2, here only e2, and this is a power sum symmetric polynomial based on lemma again. This can be expressed in terms of e1 and e2. This can be expressed in terms of e1 and e2. This is a constant, that this is written in terms of e2. Again, the total expression is in terms of e1 and e2. It's as a polynomial in terms of e1 and e2, yes? Again, pm minus n can be expressed as a polynomial in e1 and e2 based on the lemma. Okay? And it might happen that all these possibilities actually arises in your polynomial. And of course, each part individually can be written as a polynomial in terms of e1 and e2, and then it is completely clear if I combine them, either add them or subtract them, the result still would be the same. So we were able to show that all symmetric polynomials, not only the power sums, can be expressed as a polynomial in terms of e1 and e2. And you saw that when I wanted to prove this theorem, in two cases I used something from the lemma. If I haven't done the lemma before, I have to bring the proof of that lemma in the proof of this theorem, makes the proof of the theorem longer. So this is of course subjective. Some mathematicians probably think that we can bring that proof here, so the proof would be longer. Some people think that let us break it into steps, and then if they do this, the theorems that the true statements coming before the main theorem, they would call it lemma. Okay. And then one thing that is very important, it is writing this polynomial, writing a symmetric polynomial in terms of E1 and E2 is unique. It doesn't matter how you start doing it, either the way that we did it here or any other way, it is always coming to the same answer. But proving the uniqueness is technical, so I just want to skip that one. Okay? Now let us go back to factorization and see how this might help us to factorize some polynomials. Of course, if the polynomial is symmetric, because what we talked so far is only for symmetric polynomials. Okay, let us consider this one here. Example 1715. Consider the following symmetric polynomial. Of course, it is easy to convince yourself that this is symmetric. If I interchange x and y, this will go back to this will go back to this, and this remain the same. So you see, exactly these are the possibilities that I was talking here. You see, if 2x4 appears, definitely you will have 2y4. And if something like this happens in the last step, where the powers are different, so you will get something like this. Otherwise, it is not symmetric. And it might happen that you have a term like that, where the powers, where the exponents are the same. Okay, so the first thing that we want to do is to write this in terms of E1 and E2. And it is possible, yes. First of all, it is guaranteed by this theorem that this is possible. It's also guaranteed by this theorem, if you can write it in one way, this is the only way because of the uniqueness. Okay, and then how should I do that? I need to follow more or less the same strategy. So I will write q of x and y. I realize that these two terms, I can factor the 2 out between those two. So I will factor 2 out. It becomes x to the 4, y to the 4. And then I will have this term. So let me combine them here for you. So I took this one with that one. I will take these two together, and you see that 5xy is in common. So I'm using exactly the strategy that I used for the proof. You see, I took these two types of terms together, these type of terms alone, and these type of terms together again. Okay, so I took these two together, and leave this alone. Yes. So then what happens? It becomes, I take 5. Let me change the color. So I factor 7xy out from these two terms, and then x squared from the first one and y squared from the second one are left, and then I have this 9x squared y squared alone. Yes, that I can write xy to the 2. Okay, let me write it in the next step. So let me write x to the 2, y to the 2 for the time being. And then, of course, immediately it becomes clear that this expression is just P4, power some symmetric polynomial of degree 4. And this is P2. And this is E1. And this is E1 to the 2. This is E2. And this is E2 to the 2. Yes. So let us write this down. So this becomes 2P4 plus 7E2 P2, and then 9E2 to the 2. But P2 and P4 are expressible in terms of E1 and E2. Yes. So let me go and write this down. If you go back here to the table, you see here, we have already done that, by the way. So this is P2 and this is P4. So I will use these formulas in what I have on the next page. Okay, so then what happens? This becomes equal to 2 times, instead of P4, I use the formula from the previous page. Okay, this was the formula. Yeah, let me double check. Yes, so that's correct. And then the next formula, plus 7E2 P2, I have it in my memory, so this is E1 to the 2 minus 2E2. And then finally I have 9e2 to the 2. And now let me expand and simplify this expression. Okay, so this becomes equal to, I multiply the 2, it becomes 2e1 to the 4 minus 8e1 e2 plus 4e2 to the 2. And then I multiply 7e2 inside, so it becomes 7e2 e1 to the 2 minus 14e2 to the 2 plus 9e2 squared. Okay, and then you see this term is alone, so the first term is alone, but what can I write here? Oh, by the way, I missed this power 2. Here, look, there is a power 2 here, and then I missed this one here, so this is also 2. Okay, and then let us simplify. Then you see that this term and this term are similar. These three terms are also similar. So if I simplify them, what will happen? This becomes 2e1 to the 4, and then I will have minus e1 to the 2, e2, and then I will have 4 minus 14 is minus 10 plus 9 is minus 1, so it's minus e2 to the 2. Okay, so here I haven't done anything for factorization. This is not still in factorized form, of course, but I have written my polynomial, a symmetric polynomial, in this form. And this is guaranteed by this theorem that no one else can write something else. Because you see that you might think that I can have other polynomials that will produce the same q, x, and y if I replace its x with e1 and its y with e2. Okay? But this theorem guarantees that this is the only way of doing that. Okay, so now you see that, first of all, of course, this, by the way, this is no longer symmetric. If I ask you, is this generated polynomial symmetric in e1 and e2, you definitely see no. If I interchange e1 with e2, then this becomes something else. So even though I started from the symmetric polynomial qxy, but if I do these replacements, there is no guarantee that what I get at the end is symmetric. As you see, it is not. But this might be a little bit simpler for us to factorize than this form. Okay, so how can I do that? So if you don't mind, here I think you have enough experience here, so I want to use the quadratic rules, the methods that I taught you when I was teaching about factorizing quadratic polynomials. Of course, this is also quadratic in e1 in e2. Yes, so this power of e2 is 2 here. So this is why I'm motivated to factor and minus sign out, because I want to make this complete a square, and this negative sign is an obstacle there. So I take the negative sign out. So, and then I would write this one first. The second term, the middle term, I would write it as positive e1 to the 2 e2, and the last term now becomes 2 minus 2 e1 to the 4. If I can factorize it over the set of integers, then this can play the role of the common term. Sorry, e2 can play the role of the common term. So I open two pairs of brackets, I put e2 here and e2 there, and I ask myself, can I find two expressions whose sum is plus e1? So I would ask this myself. The sum becomes positive 1e12, and the product becomes, let me write it here in front of it to save space. So P, the product, becomes equal to negative 2e1 to the 4. And I don't think this it is hard to guess. Yes, so one of them is 2e1 to the 2, and the other one is negative 1e1 to the 2. Yes, let us double check. If I add these two terms, it becomes positive e1 to the 2. That's correct. If I multiply them, it becomes negative 2e1 to the 4. So that's completely right. So I would write minus e1 to the 2 here, and then I would write positive 2e1 to the 2 here. Okay, so let me separate this part. Okay, and then let us come back to the same color here. And now I multiply this negative sign inside the first bracket, so it becomes e1 to the 2 minus e2. Then I have e2 plus 2e1 to the 2. Okay? Okay, we succeeded at least in factorizing. You see, it is written in a product form now. But of course, these are written in terms of e1 and e2, but when I ask you to factorize the polynomial, you should write it in terms of the old variables x and y, not in terms of something new. So it means that I need to switch back to the main variables. So that is easy. What is e1? e1 is sitting for x plus y, and then I have a power of 2 here. So this becomes to the 2. And then what is e2? e2 is sitting for xy. I replaced it. And then again, in the second pairs of brackets, so I have e2, which is xy, and then I have 2 times x plus y to the 2. Yes? And as usual of factorization, we never leave these extra brackets. We simplify them, because it might happen that still we can continue. Okay, if I use the quadratic rule in both of them, the first one becomes x squared plus 2xy plus y squared, and then I have minus xy at the end. Here it becomes xy plus, I raise it to power 2, yes, by quadratic rule. And then let me simplify this expression so that I can take it with me to the next page. So it becomes x squared, and then look here, I have 2xy and negative xy, so I can write positive xy, and then I have y squared. And here, if I multiply that, it becomes 2x squared, and then 2 times 2xy becomes 4xy, another xy here becomes 5xy, and then finally I will have 2y squared. So far you see I succeeded in factorizing my polynomial. The only problem is that it might be not the complete one. So let us take this one with us to the next page, hopefully possible. Yes. Copy, I think I just picked some extra things as well. So anyway, I can delete that then. Yes. So let me delete this extra parts that we don't need and then bring it back higher here. Okay. Okay, can I factorize this more? This one, no. Why? Because you see the coefficients are 1. The coefficients are 1 and 1 and 1. If I calculate delta as b squared minus 4ac, it becomes 1 minus 4, which is minus 3 negative. So it cannot be factorized even over real numbers, let alone over the set of integers. So this is already factorized for if I want to continue on the set of over the set of integers. But what about this one? You have enough experience. So here delta is 5 to the 2 minus 4 times 2 times 2. And then if you calculate this one, it becomes 9. And the 9 is a complete square. So if I write square root of delta, it becomes a square root of 9, which is 3. So the roots of this polynomial are... in the worst scenario case, it is rational, so it might happen that I still can factorize this over the set of integers by the experience you got so far. But now, what can I do here to factorize this polynomial? Do you remember? You can use one of those tricks that you learned before. So I hope that you can do breaking terms. Breaking terms is easier here. It's not that hard to guess how should I break the middle term here. So let me just do it here. So 2x squared plus yxy plus 2y squared. There are different ways that I told you how to factorize this polynomial, but I want to use this way here. 2x squared, I would say that I need two numbers whose product is the product of these two, it means 4, and the sum is 5. So one of them is 4, the other one is 1. So it means that I will break the middle term into xy and 4xy. And then I have plus 2y squared. Then I take, for example, this one with that one. For example, yes, if I take x here, then 2x plus y is left. Yes, it doesn't matter. So I can take these two and I can take these two. Yes. So then what happens? If I factor x out from the first one, it gives me 2x plus y. And if I factor 2y out from the second group, it gives me 2x plus y again. And that is good, you see, because now I can factor 2x plus y out and I am left with this. Okay, so now if I put everything back, then it means that the qxy that I was looking to factorize it becomes x squared plus xy plus y squared, and then instead of this expression I put 2x plus y multiplied by x plus 2y. Yes, and then you see that this is the factorization of my polynomial, using the symmetry of the polynomial and using these elementary symmetric polynomials. Okay, our last example for today is use arguments based on symmetry to factorize the following polynomial. Yes, you see that this polynomial is evidently symmetric. Why? Because if I interchange x and y, then what I get is y plus x to the 5. Instead of x, I would write y to the 5. Instead of y, I write x to the 5. And they are actually equal. So this polynomial is indeed a symmetric polynomial. Of course, you can try to write this in terms of power sums and try to see how it works. For example, here, can I write it in terms of E1 and E2? Definitely yes, it is guaranteed by our theorem. So how can I write that? I don't want to continue this. This is why I have mentioned use arguments based on symmetry to do this. But let me just, for practice, write it like this. So q, x, and y. This is already, yes, this is already E1, so this becomes E1 to the 5, and if I factor a negative sign from the second and the third term, you will get this. But what is this? This is P5, so this is E1 to the 5 minus P5, yes, minus P5. And of course, if you go back here to the formulas, and then you can see what is P5, and you can take it back there, and this of course works. I really recommend you, after watching the video is finished, please try to do it in this way. This will work and it might be seems easier, okay? But I want to teach you something else. I want to teach you sometimes arguments based on symmetry will facilitate factorizing the polynomials. You might not value it that much here that I am talking about two variable cases. But then the next video you will see that I will talk about polynomials with more than 2 variables. In that video I will talk only about 3 variable case. And then you see that these kind of symmetry arguments facilitate a lot the job of factorizing the polynomial. Okay? So now I want you to continue. So I would write here continuation exercise. Okay, so let me write it here for you. Continue this as an exercise. Yes, you go back there and read the formulas and try to do it yourself here, okay? But now let me change my color to show that this is the solution that I was meaning for. Sometimes the form of a polynomial, of a symmetric polynomial, is so simple that you can guess how this polynomial can turn into the zero polynomial. For example, it's completely clear that if I put x equal to 0, then this becomes 0. Let us check. If I put x equal to 0, what happens? The first term 0 plus y is y to the 5. But this term vanishes because this is 0. And then the last term is minus y to the 5. It becomes 0. So then what does it mean? It means that qxy is divisible by x minus 0. But x minus 0 is just x. So we realize by this simple observation that my polynomial is definitely divisible by x. And because this is symmetric, if this is divisible by x, definitely this is also divisible by y. Let us check that. I keep x, but I replace y with 0. Then what happens? Then it becomes x plus 0 to the 5. We really don't need to check that because the polynomial is symmetric. And then I would write x to the 5 minus 0 to the 5. And then the first one becomes x to the 5 minus x to the 5. The last term is just 0 and this becomes 0. So as we could guess, qxy is divisible by y minus 0. Y minus 0, which is equal to y. Of course, you really didn't need to check the second one. There is also one possibility. It's not hard to see. What happens if I switch, if I replace y with minus x? So let me calculate this one. I would say q of x, instead of y, I put minus x. I'm not saying that this is easy. For example, for the previous case, it was not easy to seek some kind of these arguments, yes, for this case that I am here. And you see that it didn't work actually because when we finalized the problem in this form, it was not easy to guess that if I replace x with minus 2y, you see, if I replace this, then this becomes 0. But it was not easy to detect this by just looking at the form of my polynomial there, yes? But sometimes, like this, it is not that hard to guess. If you couldn't guess, of course, then you need to continue this method that I left as an exercise. It is very simple. But if you can guess, then it will actually facilitate calculating, factorizing the polynomials quite a lot. So if I interchange y with minus x, let us see what happens. So I have x here, instead of y everywhere I put minus x. So what does it mean? It means that I can write x minus x to the 5 minus x to the 5 minus x to the 5. So this is 0 to the 5 minus x to the 5 plus x to the 5, and it becomes 0 again. So what does it mean? It means that qxy is divisible by x minus y, which is x plus y. Okay, so that's enough. So what does it mean? It means that definitely when I factorize q of x and y, I realize that qx and y is divisible by x, so x should appear as a factor. It's divisible by y, so y should appear as a factor. And it is also divisible by x plus y, so this also should appear as a factor. So then it means that the form of this polynomial is this. But of course this cannot be true. Why? Because you see that my q of x is of degree 5. But this polynomial is of degree 3. Degree 1, and this is also degree 1. So the degree of this polynomial so far is 3. So they cannot be equal. So, but it means that I have also another factor which I don't know yet. Let me call it capital Q, and this is also a function of x and y. What are the facts that I know about this capital Q? First of all, because the left-hand side is a symmetric polynomial, the right-hand side should also be symmetric because they are equal. But so far the polynomial is symmetric. If I interchange x and y together, this becomes yx, this becomes y plus x, and that's exactly the same thing. So this means that the qxy should be also a symmetric polynomial. So the first conclusion, qxy is symmetric. Second, the degree on the left hand side is 5. The degree on the right hand side should also be 5. But 3 of them is here, so the degree of q of x should be 2. This is degree 3. This should be of degree 2, so that if I multiply them, it becomes of degree 5. So degree of q is 2. Okay? Now, what I can know about this symmetric polynomial, because this is symmetric, based on the theorem that we just discussed about, this should be expressible as a polynomial in terms of e1 and e2. On the other hand, the degree of q is 2. So how can I partition 2 into a sum of 1s and or 2s? Two ways. 2 is 1 plus 1, or 2 itself. But this, do you remember? This represents e1 times e1, which is e1 to the 2, and this represents e2. So I realize that q of x and y would be a polynomial in terms of these two expressions, either e1 to the 2 or e2. So what I know is that this should be of this form, ax squared, e1 to the 2 plus another constant which I don't know yet, e2. This I want you to see. This is the power of that theorem. Otherwise, how should I know that this polynomial is expressible in this form? Okay? So this means that at the end of the day, what is q of x and y? Qx and y, let me write this qx and y is equal to what is the original polynomial here. So this means that this one is x plus y to the 5 minus x to the 5 minus v to the 5 is equal to xy times x plus y, and then I have qx times y. Instead of qxy, xy, I write this one, and then I replace e1 with x plus y, and I replace e2 with x times y. Yes, so what happens? This becomes a x plus y to the 2 plus b x y. Yes, so it means that if you look here, I was able to factorize my polynomial. Yes, my polynomial is now factorized in this form. But still, these two things, these two numbers are not known. This is undetermined coefficients yet. I want to determine them. But this is supposed to be an identity, so it means that for all possible values of x and y, the left-hand side should be equal to the right-hand side. Yes? So I can use particular values. So for example, let us choose. The simplest possible value is probably 0 for x, but it doesn't work. If I put x equal to 0, the right-hand side totally vanishes because of this factor of x. If I put x equal to 0, the right-hand side becomes 0. Of course, if I put x equal to 0, the left-hand side also becomes 0. I don't come to a contradiction, but 0 equals to 0 is always true, but it doesn't let me to calculate these coefficients. So I cannot make it that simple. So the first thing that comes to my mind, let me check, for example, take x equal to y equal to 2. Then I plug these values on both sides of this equality. The left hand side becomes 1 plus 1 to the 5 minus 1 to the 5 minus 1 to the 5. The right hand side becomes 1 times 1 plus 1 times a 1 plus 1 to the 2 plus b 1 times 1. I replace x and y with 1 and 1 everywhere. Then this gives me an equation for capital A and capital B. Yes. So what is the left hand side? Let us calculate this. 1 plus 1 is 2. 2 to the power 5 is 32. Minus 1 is 31. Minus 1 is 30. And here if you multiply that, this becomes 2. Yes. So the left hand side is 30. The right hand side is 2. And if I calculate the inside, this becomes 1 plus 1, 2, 2 to the 2, 4. It becomes 4 capital A. and then I have b. And if I divide by 2, I get an equation here. So 4a plus b is 15. Okay, but this is not enough to solve the problem. Let us check two other values. I don't know, I made a mistake in writing. This is not supposed to be 2. I did correct, but I wrote it wrong here. So this is not 2. I chose x and y. You see, I chose x and y everywhere to be 1. So this is 1. Now let me take this thing, x equal to 2, y equal to minus 1. I want to keep the numbers as small as possible. Unfortunately, 1 and minus 1 doesn't work, because if I put 1 and minus 1, this becomes 0, and then I will not get any information for a and b. But let us keep the numbers small and see that how I can simplify this. Okay, so let us do 2 and minus 1 here. Okay, so if I put 2 here and minus 1 here, what happens? It becomes 1, and then to the 5 it becomes 1. So let me just simply write it 1. And then I have 2 to the 5, which is 32, and then minus 1 to the 5. So it becomes positive 1 again. So it becomes minus 32, positive 1 on the left-hand side. What have I on the right-hand side? On the right-hand side, I have x here and y here. If I multiply them, it becomes minus 2. If I add them, it becomes positive 1, so I get minus 2. Yes, it becomes minus 2. And here I will have 1 plus 2 plus minus 1 is 1. To the 2 is 1, so I will get just a. And the next one becomes minus 2b. Yes, and if I simplify this, the left-hand side is minus 30, and if I divide by minus 2, I get again positive 15, so I will get a minus 2b is positive 15. And now I solve this system. 4a plus b is 15, a minus 2b is also 15. This is a very simple equation. You can solve it. If I multiply the first one by 2 and add it here, I will get a equal to 5, and if I put a equal to 5 here, I get b equal to minus 5. Yes, it's minus 5. Yes, so I got my answers for a and b. Then what is left is just plug these numbers back here and see how it goes. So then the q of x and y, which I was looking for, was x, y, x plus y. And then instead of y, I put 5, x plus y to the 2. Instead of b, I put minus 5. It becomes this one. But again, I immediately see that 5 is a common factor now, so I can pull it out. So it becomes 5xy, x plus y. And then what is left for me is x plus y to the 2 minus xy. But I told you that we never leave these extra brackets, so I will remove this one by using quadratic rule. So this becomes xy, x plus y. So then it becomes x to the 2, y to the 2, 2 times xy, then minus xy, it becomes positive xy. So it becomes x squared plus xy plus y squared. Sorry for this little space. So yes, this would be our final answer. Of course, if you go back and continue this method, this would be much simpler in this case. But these kinds of symmetry arguments, my goal of solving this problem this way, I want you to learn these kinds of arguments. These are really important if you want to solve some harder problems. Here, for example, if I just want to understand what is the general form, I could immediately guess this general form. Okay, I really didn't need to continue if the general form was example. So this calculation got a little bit messy because I wanted to fine-tune those coefficients. Okay, so I wanted you to see, because when we are talking about factoring polynomials, this is one of those methods that I wanted you to see. Okay. We will be left with one more video for factoring polynomials. I will talk about the same material that I covered in the second part of this lecture today, but instead of having two variables, I will talk about symmetric polynomials in three variables. And then we will finish this one and we will continue the advanced high school algebra, which I would call even might be it's a little bit more advanced than college algebra. And even some university students might not know these stuff. But anyway. Okay, we will talk one more video about factorizations and then we switch to a new topic. I will decide about the new topic later. Okay. Okay, until the next video, take care and goodbye.